Okay, we're going to talk about the processes responsible for plume attenuation in oil sands. So this is a sort of a mid-project perspective as we keep developing this this project. I'm going to skip through the abstract. People can read that at their leisure if need be. Okay, the project has a lot of people. Jason, who was just there, is a major player, same as James Yang. There's a couple of students, Samuel and Stephanie. Martine, who is now retired and hopefully enjoying her retirement well, has been a major player in this. And there's a bunch of GSC support staff, from Gilles and all the crew at GSC Quebec to all the lab staff here in Ottawa. Universities, McGill, INRS, Carleton, Ottawa, all have parts in this. John Headley and Kerry Peruti, Athabasca Oil Sands Companies. So the question I'm really wanting to do is, what happens when OSPW enters natural boreal systems? OSPW is oil sands production waters. So this is the stuff that ends up in the tailings ponds, these very, very large tailings ponds. And what happens when it escapes? Because we all sort of believe that it escapes, but there's been very few studies on exactly what happens. And so we're trying to answer this via development of a reactive transport model, a very difficult, time-consuming numerical model of the interactions between OSPW and natural systems and natural matrices. So I'm going to start by looking at reviewing some of the stuff we went over last year, but just so that people are more familiar, this is the site. That's 90 meters, so it's a small site. This is all our drive points and sampling points in this wetland. This is a wet spruce forest, sort of surrounded by dry forest there and dry forest there. This is sort of forms a little basin in and of itself. This wetland fen was formerly a meander bend of the Muskeg River here. You can see the tailings ponds just in the very top left-hand corner there. And so this site we've chosen because basically we can find the oil sands production water coming into this site at this seep here. And keep this seep in mind, because I will refer to that as sort of the geographic locator through multiple slides. But that seep is actually pretty much production water coming to the surface. Oops, just let me get rid of that. Okay, and to give you an idea of what this site looks like, this is a transect across here. And this is a hydrostratigraphic model, not a geological model. Sort of they follow each other. And what you have here is the modern Muskeg River with its modern levee, and you have this basin behind it, which is full of organics. And sitting below it are these river sands, these river deposits. And so essentially what you have is an organic aquifer and a sandy aquifer within this wetland, separated by a mud aquitard. Now, if in the numerical hydrological model, that muddy aquitard in this diagram looks consistent, but in fact it's actually pretty leaky. And so when we actually model this, the water from the seep comes in at the thing, moves through the wetland, and then moves into these very 10 to the minus 3 centimeters per second porous and permeable sands at the base. If you actually look at the flow paths and the fluxes, what you see is that the waters take this arcuate trend. They go subsurface about here for the most part, and then end up in the river in about 3 to 6 years, depending on the path they take. What sort of we look at when we see this is the thing that we really look for is the boron values, because it forms this beautiful contour, 400 ppb, 300, 200, 100. It's actually almost a textbook bullseye pattern. And there's really only one source of boron in here, and that's the tailings pond. There's no other thing. The background levels are 20 to 50. So 400 is, and the tailings pond is around 2000. So these kind of levels, there's really only one source, which is why we're pretty confident this is OSPW coming into here. But what's really interesting is that attenuation is very rapid. Within 60 meters, the boron is pretty much gone. We have a whole bunch of other analyses ongoing, but that's the real basic outline of this, is that we've got this seep coming in, and it's clearly attenuating very fast. If we also put potassium up there and put the two together, the boron and potassium contours look actually quite different. And this is sort of something that puzzled us for a little while until we started really getting to grips with it a bit more. So the question obviously is, well, what is more representative dilution? Is this purely a dilution? Because again, what we're trying to do at the moment is really identify the processes we need to model in the reactive transport model. So dilution is obviously going to be one big process that we need to understand. Now, potassium is definitely a more mobile, prefers the dissolve phase than boron. So if you actually consider the potassium as a more reliable indicator of the dilution, then you can use these two against each other to start understanding what kind of attenuation rates you are looking at. And here's the attenuation contours for boron. These are all surface waters, but keep in mind that there is surface groundwater communication here, and this is the preferred groundwater communication transport path through here, and then it comes down through here, in fact. But for within this contour pattern, this is the preferred path. So you actually see that the contours themselves are actually following this preferred path, as you would expect, because that's sort of pretty much following the topography to some extent. But what's really interesting is that compared to dilution as measured by potassium, you get over 100%. That means that there's something other than dilution going on, that this must be some active attenuation that's making these kind of 120% in comparison to dilution. Of course, you can't get more than 100% dilution, so that extra 20% must be from something else. What's also really interesting is that you get this zone here, which we puzzled over for quite some time, and I don't know why, because it's not that difficult, as to -40. So that means this is suggesting that you're actually getting boron desorption, and boron, this is actually acting as a boron source for the water movement through this wetland. So how can that actually operate? Well, if you actually, I'm going to, at the risk of being too detailed, this is essentially absorption desorption equation. Aqueous boron, dissolved boron, enters the substrate, and if it gets sorbed, you get boron with the substrate plus water, and desorption is the opposite process. So if you're at equilibrium and you add water, you drive the equation this way, and you actually end up with desorption. That's essentially what was happening. This year that we sampled was actually a pretty wet year, and so I suspect that what this area here was actually truly acting as a source. The interesting thing about that is it's actually indicating that you're actually at equilibrium here, that in fact the boron dynamics in this area is actually an equilibrium dynamics. And then you can start working with something called KDs, which is essentially the boron concentration in the absorbed phase versus the aqueous phase. Now we have those measurements, and so we can actually start producing a mass balance model of that. And what you find is that if you actually go from the distance to the seep, your KD starts off through there. It's very consistent with what you should get, what the literature suggests you should have for these kind of systems. But then as you get to the edge of the seep and into the fen, you're actually seeing that the KD skyrockets, because essentially you've got way more excess boron absorption capacity. So this is confirming pretty much that what you're looking at is an equilibrium dynamics within the actual plume. You can go one step further than that, and it's something that's sort of important for understanding the history and the length of time. And you can make a few assumptions and start thinking, how much of a boron flux do we have? So if we take the hydrologic model that we've generated and understand it with these partitioning coefficients, it suggests that the seep has been active for 13 years. And given the assumptions and the variability, the tailings pond's only been active for 20 years. That suggests to me that essentially what we're looking at is that this seep has been active probably since the ponds were instigated, since the tailings pond was instigated. We can take that a little bit further, and now we'll get on to some of the data that was actually produced in the last year, which is the acid extractable organics data, and it sort of follows on nicely from what Jason was saying. There's a couple of different ways of playing AEO data. One is O2 to O4 ratio is considered to be an OSPW signature. So is an O even to O odd ratio. So that's a long hydrocarbon chain with even number of oxygens versus a long hydrocarbon chain with odd number of oxygens. That ratio is considered to be indicative of tailings pond water. And you see that it doesn't really matter which one I plotted. They both sort of show the same thing. The tailings pond is around 3.5, and that's that ratio. Muskeg River is 0.95. At the seep, it's around maximum at 2.7. So it's dropped 0.8 between over this 100 meters between the tailings pond and the seep. Yet in this 10 meters here, it drops another 1.2. That's whereas in the boron, the reaction front was was right out here at the edges of the plume. Within the AEOs, there seems to be a very, very strong reaction front right at the seep locality.
Paul, we lost you. Hello, Paul?
That's PW.
Oh,
Whereas here it's up to 80%. So this is generally consistent with the plume as defined by potassium. But it's also inconsistent with the dilution and sorption processes with the inorganics. So the attenuation is clearly not uniformly distributed. It suggests a reaction front right where the seep is. And the reactions are clearly lessening the OSPW signature. That's really interesting because it obviously means that the naphthenic acids, which are considered the nasties within the OSPW, really are being strongly attenuated in this system. Why it would be obviously a wonderful thing to know. You can go a little bit further than that, and again, the distance from the seep. This is the AEO in the blue, total AEO milligrams per liter, and then O even and O odd in milligrams per liter. And as you can see, this actually decrease is mostly taken up in the O evens. O odds basically consistent across the plume, whereas the O evens drop dramatically in those first 10 meters. This represents, if you actually do absorption calculation, it represents a KD of 25 in the first 10 meters. Well, literature values, what they are, take that with there's very little literature data to start off with, but they suggest much more in the vicinity of 1 rather than 25. So it doesn't suggest that this is a sorption system. It's more likely exchange and decomposition or decomposition. We can look at that a little bit more detail in AEO exchange. So here's some chromatograms that I've put on their side. This is the M to Z number, on similar scale, and then a relative abundance on this scale. And what this is the seep proximal, so this is right at the seep. It's enriched in these lower M to Z compounds, and whereas distally it's impoverished, and vice versa. That suggests to me that what we've got is a pretty strong exchange process. That in fact what you've got is that the even oxygen AEO components are basically competing for absorption sites within the organic matrix of that, and swapping out components that were already there. This will hopefully, the isotope data will really help clarify exactly how that's happening. We're also getting microbial eDNA data, and that will help us understand whether decomposition is playing a significant role here too. We're also going to get toxicity data when labs open up. So the obvious question we've got to ask is this exchange, is this sorption actually changing the toxicity of the seep waters? Other processes that we've identified, there's high alkalinity throughout the site. Many carbonate minerals are well above supersaturation. It's not restricted to, it's not located at or near the seep. It's essentially throughout the site. Is that our organometallic complex is being impacted by that, by the carbonate saturation and almost certain precipitation in this site. So that's something else we've got to model. Oxyhydroxides, this is a relative depth versus concentration. And what you see is that in the quartz sand aquifer, there's quite a range of oxygenation states. Whereas once you get into the organic aquifer across this muddy barrier, you've got high Fe2+, quite reduced conditions that by the time you get to the surface is oxidized. And often when you're digging auger wells in there, you find reddening in the sort of 20 to 40 centimeters below the surface, suggesting oxyhydroxide precipitation. Again, that's the sorption dynamics and the dynamics of those are pretty well understood, and the literature will help us model those. Some sites also have aluminium oxyhydroxide supersaturation. Whilst how significant is that is sort of a bit unknown, but aluminium oxyhydroxides have very high surface charges, so they can be very important components if you have them. So it's something we'll spend a bit more time investigating.
Oh, super.
In summary, the research side is now well characterized. Some data is still outstanding, but that's COVID for you. A hydrologic model is pretty much complete. That's a critical underlying component of the reactive transport model. The plume environmental chemistry is becoming more clear. Dilution calculation currently uses potassium. It's not perfect. We might try and see if recalcitrant dissolved organics may be better. We'll see. Boron concentrations within the plume are controlled by equilibrium sorption dynamics. It's a textbook case. It really is wonderful. And again, from that you can we've determined that the seepage probably has been there since the advent of the tailings pond. The AEO data indicates extremely strong attenuation. There's the processes of almost certainly exchange, and sorption, but possibly decomposition as well. And there's a whole bunch of carbonate and oxyhydroxide minerals that we've got pretty well constrained to, and that will help us understand organometallic component. Thank you for listening.